So on Tuesday, we basically got an introduction of BJTs as we went through the physics of the physics behind BJTs, where you have this two p-n junctions from base to emitter for NPN. So we have two types, NPN and PNP. A lot of them are going to be dealing with the NPN type or N type, sometimes short as N type BJTs. And then there's a p-n junction from base to emitter, what looks like a diode, and that has to be forward biased, to have current to flow. There's a p-n junction from base to emitter to collector, which is reverse biased, and in fact, it's working in the breakdown mode. Because it has two p-n junctions, so we call this bipolar junction transistor, so BJTs, bipolar, so it's like two p-n junctions. And within the BJT, we have a couple important equations. For example, we have emitter current equal to basic current plus collector current, and then we have emitter current also equal to 1 plus beta times IB, and that beta value typical is about 100, but of course sometimes it's 50, sometimes it could be different. So when you do a problem, if the beta is not given, you can always assume it's 100, okay? But sometimes the problem says assume beta is infinity. So what it means that when you assume beta is very big, it means the current in the base can be neglected. So that means IC and IE almost is identical. But in fact, even beta at 100, IC and IE difference will be 1%, right? So it's very small difference between IC and IE. So oftentimes that we assume beta to be infinity, or we assume IC/IE the same to do the problem. But when we calculate IB, we go back saying, okay, so beta is 100, now we get IB is like 0.01. So that's how usually we work. And then we have three different operation modes. There's a cutoff, which means VBE is less than 0.7. So that diode between base and emitter is reverse biased, so no current flow whatsoever. And then there's a linear region, sometimes also called active region, where you have the current, which is almost constant for a given VBE. So this current are proportional to VBE. And when you apply too much current, and then the current actually goes down, which means you get to the saturation region. Now, remember, this saturation region is not the saturation region of MOSFET. MOSFET saturation region is here, and there's this region we call triode. But in BJTs, we call this region a saturation region. We call this either a linear or active region. So this is the area that we use for amplifier. Okay, so for that summary, I reposted some of the equations here. As you can see from the top, base current, the IC over beta, and again, beta is about 100, typical is 100. But of course, it can go from 50 to 200 depending on the BJT design. And then because the BJT is like a super node with 3 nodes, with 3 branches, right? You can have a super node. So therefore, IE is IC plus IB. And because that equation, you can plug in that beta or IB to the second equation, you can get another equation, which is IC equal to alpha times IE. Alpha is beta over beta plus 1. You can see that if beta is 100, alpha is about 0.99. So IC is about 99% of IE. So IE is bigger. IE is always bigger, no matter it's PNP or NPN. Okay. And these are typical circuits for N-type BJT. And this is a typical circuit for a P-type BJT. You notice that, yeah, go ahead.
It's a really big number. Do we ever assume that IB is 0?
You do. You do in the sense that if beta is not given, they say beta is infinity, you can assume beta is 0. But of course, later on when we get to small signal circuit in chapter 7, that's where you can really set IB 0. But you can still say that IB for the large signal, which we mean for the DC operation, is approximately 0. Yes, that is okay. Again, depending on what the problem is asking for. Yeah. As you can see from if it is p-tau BJT, we totally like change the drawing, but we still have the current flowing down from up to lower direction. So this way, you can see that E is flipped, right? E is up now. So E is on top and collector is at base, at the bottom. And base is still on the other side. You can see clearly for this p-tau BJT to conduct, you would have VEB larger than 0.7 or equal to 0.7. So it's VEB, no longer VBE. So in this case, it's VBE, you see, but in this case, it's VEB. And also, if the transistor is active or in saturation mode, you have VEC is a certain value. But in this anti-BJT, you have VCE is either 0.2, 0.3, or whatever that value is if it's in active mode. So that's what you would see. Now, how do you calculate IC? That's what this equation over here gives you is IS times e to the power VBE over VT. So that equation is exactly what we got for diodes before. Then IS can be calculated based on the semiconductor property, which equal to a bunch of parameters. So if we ask you for IS, apparently we'll have to give you all these parameters. All these like new number of electrons, widths, depths, and things like that. So we don't really do a lot on this one. A lot of the problems, I would say 99 of the problems are given, IS is given. So you don't have to really calculate IS quite often. Maybe one problem asks you for IS, but most other problems don't. Okay. So this is a kind of a summary. And because the way that we have these relations, like IB equal to IC over beta and so on, we can draw a equivalent circuit of this BJTs. So the way to draw the equivalent circuit is like this. There's like 4 different ways to draw the equivalent circuit. The first equivalent circuit over here, as you can see, we represent VBE as a diode. That is a PN junction, right? So it is actually a diode. So we do that. So it's like a diode between VBE. So in order for this transistor to be conducting or to be working, the VBE apparently has to be 0.7 or sometimes we'll say about 0.5. That's how it works. And then you have a collector current is equal to over there. That's the equation IS times E to the VBE over VT. That's the current in that collector, right? The difference of these two current is IB. So this is a very simple equivalent circuit for a BJT. Now, because there's a relation between IE and IB and IC, so therefore we can transfer that circuit to this one. It's the same circuit, but simply replace the numbers, like R times IE, for example, and IE is here and IB is here. So right, so nothing really changed. So that's kind of what we call this one in the future. We call this T model. We use this as a T model, like it's like a T. That model is good, but sometimes it's not very convenient to use. So therefore, we transfer that model into another model, and this is called a pi model. And of course, in a pi model, will be for small signal, it looks similar, but it's very different. Later on, we'll deal with it. But in the pi model, you see IB comes in, and again, there's a diode over here. And from this current, which is IS times E to the VB over VT, that's the current through this one. Once you have IB, this induces the current in collector, which is this one here. So as you can see, so this IC is related to VBE, so which means VBE here. So IC is a controlled current source, okay, or dependent current source. And that dependent current source is depending on VBE, okay? And when you add IB and IE, IB and IC, you get IE. So this is really a mathematical representation of what we have. And similarly, this one here, we simply change this number to beta times IB, which is IC again, and right, then this is IE. So IB plus IC equal to IE. And this is IB coming in, this is beta times IB. So the difference between these two, is that here we calculate beta times IB, which means if we know IB, we can calculate current here. But for this diagram, is we calculate IC based on VBE. So which means if you know VBE, you use this equation. If you know IB, you use this equation. They're identical, but just what this current source is depending on. It's a dependent current source, right? So this is dependent on IB, but this is dependent on VBE. So it's identical, really just the equivalent circuit. Yeah, go ahead.
What's ISE in the top left?
ISE, it's just SE. It should be just SE, but it's related to IS, so it's called ISE. So
Is it what is it for? What does it like do?
What does it do? It's just a current.
Is that IE?
It's just IE, yeah.
It's just called ISE for
Yeah,
some reason?
yeah.
Okay.
Because it's related to IS.
Okay.
That's what I want you to say. Okay, the IS here is IS plus IB is equal to IE, so they call it ISE.
Alpha is the
Alpha is beta over beta plus 1, right? So if we summarize over here, I want to write down like here. So, and if you know beta is given, right? So alpha equal to beta over beta plus 1. That's if beta is 100, alpha is 0.99, right? So then you have IS equal to IC equal to IS times e to the power VB or VT. So that's the basic equation that you have for a BJT. So let me make this a little bit better. Just no confusion. Right, and then you have say IC also equal to beta times IB, right? So in this case, you would say, okay, so what is IB then? Well, IB is, you can write it down as IS over beta times e to the power VBE or VT, right? So that's how you write it. And then you also have I equal to IC plus IB. So that you can say that IC equal to IE minus IB. And then you can write down this as alpha times IE. Okay. This is some just the basic equations that we have for a BJT. Now, using all these equations and maybe even the equivalent circuit, we can solve for different variations of a BJT circuit. And that's exactly what we're going to do like over the next couple of say lectures. We're going to do just like we did in MOSFET, we're going to go through different examples and different variations and combinations so that we understand how BJTs work. So do you guys have any questions on the equivalent circuit? So the equivalent circuit is basically just a mathematical representation of a BJT, but including a little bit of physics because there's a diode, right? So that's why you see there's a diode. Yes.
So it's differently based on what variables you have?
Yeah, you're right. I mean, this identical circuit, it's just how to represent the current, right? In this case, you know IE, so you use alpha times IE, but in this case, you know VBE, so you use VBE to get IC. Okay, so moving on, go through examples. So this is why this one doesn't go away? We'll put it here. Normally, okay, now it goes away. Okay, so this is a typical like operation of op-amp. What is given? Like what's given? IS is given, beta is given. So those are the two basic parameters of a BJT. Those are given. And then it was saying that, okay, we got a 5 volts DC power supply. and with a resistance of 3 kilo ohm resistance at the collector, and the emitter is grounded, and there's a current of 10 microamps at the base, right? So for this given conditions, we can draw the circuit, right? We have the BJT now. So what they are saying is you have a resistor connected to 5 volts, and this is a 3K. And this one is grounded, and this one has a current source of 10 microamps.
It also connected with 5 volts at the other end.
It doesn't matter. We don't know. It didn't say. So it's some sort of power supply. Yeah. So what's given? We can write down. So what's given is 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 given. Oh. So IS is given is 10 to the minus 15 amps, very small number, yeah? And beta is given at 100. And IB is given, well, I already wrote there 10 microamps. So, and then also it says in active mode. You guys are going to hear a lot of this active mode, linear mode, and so on. So it's active mode. Well, I mean, you know that this thing, because there's a current going through the base, right? So this thing has to be either in the active mode or in the saturation mode. It won't be in the cutoff because there's current flowing. So the transistor has 3 modes: cutoff, BJT has 3 modes: cutoff, saturation, and active mode. So when there's a current flowing in the base, it's conducting. But we don't know it's in the active or it's in the saturation, right? But this problem did tell you that it is in the saturation mode. So if it's in saturation mode, and they want you to find the current and so on. So let's look at how to calculate IC. So we know that IC is equal to, IC. I was saying IC, but I wrote IS. So IC equal to S times E to the VB to the VB over VT. Okay, VT was not given, so we would assume VT is 25 millivolts. So now when VT is not given, you can always make that assumption because it's typically a constant. Now, there are 2 ways to solve this problem. Now, I'm going to go the harder way, and I just want to compare with the simplified way and see what kind of difference we're gonna see. Okay, so if we find from here, IS is given, but VB is not given, so we cannot really find IC from this equation, right? So what you have to do is to go find because IB was given. So from here, we can say, okay, so beta is 100, IB was given as 10 micro. So we have what? 1,000 micro. We got IC is 1 milliamps. So from here we got IC. Then now we look at this equation here with IC was given, IS is given, and VT is given. So easily you can find VBE, right? So let's see. So VBE is, let's take let's do some here. 1, 2. Well, I'm just going to write down the steps. So just lay down for you guys.
So is this often like what we do? We just find IC 2 different ways and solve or whatever.
Yeah, well, sometimes it just changes the order, right? Sometimes given IC, maybe find, given VBE, find IC, or given IC, find VBE. So, I mean, it's just flip over and back and forth. So let's do this. So I just want to go through the process so you guys know where this is coming from. So we divide IS on both sides. So we get ICOIS equal to VBE over VT. And we take a logarithm on both sides. So we have log IC over IS equal to VBE over VT, right? So here we have VBE equal to VT log IC over IS. Now you plug in the numbers. The one thing you have to be careful is IC is milliamps, right? IS is 10 to the minus 15 amps. So those two units has to be consistent for you to get the correct number. And VT is 25 millivolts. So you have 25 now milli times log. So IC is 1 milli, which means 10 to the minus 13. And IS is 10 to the minus 15, right? So you plug in all the numbers, what you get is 0.69. 0.69 volts. Okay, so this is actually not bad. Remember we said 0.7, right? Which means this actually is pretty close. So 0.69 volts is the actual voltage. So if you did assume that VB is 0.7, it wouldn't be too wrong. So, but of course, for this particular problem, you cannot assume 0.7 because what we're doing is asking you to solve for VBE. So once we find VBE, we need to find VCE. So VCE is here. Now we found VBE. Of course, VCE is easy because I'm going to redraw the circuit here. So make it easier to. So we know that IC is given. We calculate the IC, right? So 1 milliamps. So now you can actually calculate VCE equal to like what we call VCC. So VCC minus IC times 3K, right? So VCC is 5 volts minus 1 milli times 3K. That gives you 2 volts, which is larger than 0.3 volts. So it is in active mode. So this actually confirms that this circuit is in active mode. So we got the solutions to find VCE and VBE, so we found it. Now let's go back to the equation here. It was asking you that replace the current source with a resistance. Yeah, what the current source? The current source is one that flow into the base. So replace that current source with resistance connect to a 5 volts. Now you only ask whether it's voltage source. Yeah, now okay. They're saying, okay, I don't have a current source, but I have a resistor. I got the 5 volts already available. So I want to connect that. And then they want to ask you, what would be the value of the resistance, to get that 10 microamps, right? Yeah, just so for. Right. So what you're having here is that they're saying this is 5 volts. There's a resistor. So now they're both 5 volts. Okay, so this is ground. And this is RB, because it's RB, this is RC, okay? So what we found already, right? We found VBE already. So VBE was found to be 0.69. So now you can see that IB is equal to what? To VCC minus VBE divided by RB, right? So from here, you can say RB equal to VCC minus VBE divided by IB. And VCC was given at 5 volts, minus VBE was 0.69 volts, divided by IB is 10 micro. So from here, you can get what is 4 431. So 431 kilo ohms. Oh yeah, it is a big resistor at the base. At the base, it's always big because the base current has to be like small. So now this is how we get the problem solved. Now in this process, we did draw the circuit with the BJT, but we did not actually use the equivalent circuit. Now, if you guys wanted to use the equivalent circuit, you can do that. So let's move on to see, okay, now with the equivalent circuit, we replace the BJT with a model, mathematical model. And that model has base emitter grounded and base connected to a 10 microamps of current, and the collector connected to a 3 kilo ohm resistors to a 5 volts source. So if you do it this way, you can see that let's do on this one. This is actually part 1, right? So this is part 1. You can say that VBE is going to be 0.7 volts. That's what they're telling before. And IC equal to beta times IB equal to 1 milliamps. And then we have, oops. Sorry about that. So IC. So then we have VCE equal to, and then 5 volts, again, minus 1 times 3 is 2 volts. Yeah, so this is by like using the model, assuming VBE is 0.7 volts. We didn't go through the process of calculating VBE. And then on the second part, it's asking you for what is the resistance of RB. Now, in this case, because we assume VBE is 0.7 volts, and then our RB will be like 5 volts minus 0.7 divided by IB is 10 micro. So what we got? 430 kilo ohms. As you can see here, the difference is only 1 kilo ohm out of 430. So it's very, very small number, less than 0.25%, right? So it's not terribly wrong by using a model, by using ideal model, or by using like VB is 0.7. So we can do that. So when you guys get a problem, you will look at, okay, what I'm asking for. If you're asking for calculate the accurate VBE, you would use the equation on the previous slide. If they were asking using like a ideal case, well, VB is given, things like that, you will do it this way. Okay, so you wouldn't say which one is wrong or right. It's just based on what conditions are given. It's like somebody taking a shortcut. You couldn't say he's wrong. Okay. The one that we saw earlier, you saw that we have this BJT is a 3 like a piece of silicon together. Actually, in real manufacturing, that's not how BJTs are made. Unfortunately, that's for illustration purpose only. In real life, when they make a BJT, this is actually very similar to how they make a MOSFET. So they have a piece of silicon, and then they dope the silicon to make N material, which means it's a negative, like a lot of electrons. They dope the material with impurity. And then on that silicon, they dig a well, and in that well, they dope a different material to form P-type material. And then on that P-type material, they dig again another hole, another well, they call it well, like they dig it, and then they put N material. So now you have NPN to form like this, right? And then base in the middle, and E is on top and a collector on this side. Between each of this silicon, there is metal to collect current. Now, if you guys recall MOSFET, the difference between a MOSFET and a BJT, I mean, it's quite dramatic, but there's some similarities. I can draw the MOSFET here. So a MOSFET is like this. In a MOSFET, they dig 2 holes, right? So, and then they have this metal. One of the major difference is the gate. In a MOSFET, the gate, between gate and this body, there's a silicon oxide. So which means there's no current between gate and then this body. But for BJT, the base is the metal is directly connected to the p-type material in this NPN type. So there is a current. So you see, this is one of the major differences. So that's why this is called insulated gate. Sometimes they call it insulated gate. So the gate is actually insulated. There's no current flowing normally to these devices. And of course, the other difference will be structure-wise is that you have also like p-n junctions here. You have p-n junctions here. So you also have 2 p-n junctions in this device. Yeah, go ahead. BJT what? BJT is a semiconductor device. MOSFET is everything is a semiconductor device we're talking about. The difference is here. The gate has a silicon oxide as insulator. No, silicon oxide is an insulator. It's not a semiconductor material. Silicon oxide is an insulator. It's not a semiconductor material. So that's why there's no current between gate and body, because this silicon oxide insulates. The semiconductor is silicon plus minority, plus impurity. It becomes semiconductor. Okay. So there's a difference, silicon oxide and silicon. They're different things. Yeah.
Even though the BJTs have a significantly more simple structure, why
Yeah.
would people select to use a MOSFET?
There are too many advantages.
Okay.
One of them, for example, you don't need current to go to the gate. You only need voltage to drive. Right? In the BJT, you always have to inject current into the base. But injecting current is okay, but there's always losses associated with it and then other things, right? So that's one major advantage is MOSFET does not need a current to drive the device, right? That's one advantage. Another advantage is that BJT needs at least 0.7 volts at the base to emitter to make it conducting. So you need high voltage. But in MOSFET, what we need is VGS larger than VT. Remember, right? So VT can be as small as 0.1 volt. So you need only like very small voltage to make it conducting. So MOSFET, in the sense that it's a lot cheaper to make and there's a lot lower power consumption because the voltage and current was very small.
So for an application like a large, mass storage device,
Yeah.
do you see more MOSFETs then?
Exactly.
Okay.
Yeah. I would say the modern electronics, the motherboards, the computers or storage, pretty much everything is MOSFET. 99%, maybe even more. Yeah. Yeah.
How are MOSFETs cheaper to manufacture if they're more complex?
Oh, you mean the MOSFET is complex than BJT? Yeah, well, it depends on, I guess, silicon is basically free. You can get it from the beach, right? So it's primarily the manufacturing cost to make them to become a silicon wafer and adopt them and then become so once you have the system up, it's a manufacturing process, how much effort takes to make that device. So, and also become the quantity, how many you produce, right? So once you get to a certain quantity, really the per piece price drops significantly. So there's no big difference between these two. Yeah. Okay. So it's very interesting device. And if you read in our book, there's a little note at the chapter talk about who invented MOSFETs, who invented BJTs. You know, BJTs invented in the 1940s, and it started to dominate in the 50s until the 70s. But then MOSFET was invented around the 60s, or maybe even, yeah, in the 60s, but it was not working until the 70s. It started, oh yeah, actually we can make it work somehow. And then later on in the 80s, the MOSFET started to dominate. And nowadays, MOSFET basically dominates pretty much every very large VLSI circuit, yes, integrated circuits. So the BJT, the people who invented BJT also got the Nobel Prize. 3 of them at the time. And then MOSFET too, I think they also got some, not sure, but I think they got the Nobel Prize as well. Very big invention in history. Okay, so now these devices, mostly of course we're interested in the linear mode to build amplifiers, but certainly in certain applications we're also interested in the saturation mode and then the cutoff mode. Like when we use them as a switch. So as a switch means it's either on or off. On means in saturation mode. Off means it's in cutoff mode. So this shows you how it can work in the saturation mode. So the saturation mode basically depending on the voltage of VCB. So if VCB is big enough, this one is going to work in the active mode. When VCB reduced to below 0, basically below 0.4, it started to go to the saturation mode. Okay, so this is VCB, now VCE. Okay, so it's yeah. So so let me draw actual a device so that actually we have a device. So this is the voltage VCB, and this is VCE. So when it's in saturation mode, VCE is about 0.2 volts. And VBE, of course, is in 0.7 volts. So in this case, what do you conclude? So VCB is going to be VCE minus VBE, that's minus 0.5 volts. So VCB actually becomes negative. So what it really means that when VBE is 0.7, you start to have current flow from base to emitter. And that VCE can be a very large number, but when you reduce VCE, reduce, you still have current. To the point that VCE becomes 0.2 or 0.3 to be exact. The current started to increase much more. Okay, or actually much less, I'm sorry. So IC can no longer sustain the amount of current. So, or in other words, IB will start to increase. So the ratio is that beta, so beta in this case is IC over IB. It's going to be much less than 100. So when it's going to your saturation. So physically, you can imagine that when these things go to saturation, current can no longer flow freely from collector to emitter. So therefore, the current in collector will be less. If you maintain the same IB, IC is less, which means the ratio becomes less. So that's what it means, saturation. So it's like saturated. No more current can flow. You can only flow so much current from IC to IE, yeah, from collector to emitter. So this is called a saturation mode. And okay, so this is another diagram to look at a little deeper how it goes from like a active to saturation mode. So this is the device we have. So the device we have two PN junctions. So from base to emitter, there's a diode over here, and then from base to emitter, there's a diode over here. So basically, if you look at the bottom figure, you have two diodes. And from here to here, you have another diode. Then you connect from the bottom, right? So what this equivalent circuit says, well, we can, it's not really, it's not very good orientation in the sense that the base is over there, but this base is over here. So it's not that obvious. So, but anyway, so if you look at the base up, you get two transistors, or two diodes, not transistors, two diodes, like back to back, and base in the middle. So here on the top, you can see our base coming in, we have two diodes, right? So base is in the middle of these two positive terminals of the diode. So that's how it goes here. You know, maybe I can flip this one and then mirror it, so we'll get a better. Let's try if we can do that. Yeah. Let's see. We flip like this. We probably don't need that one anymore. So we do this way. And then can we mirror it? Yeah. Let's do it this way. So maybe this is better. Yeah. Oh, no, actually.
It has, problem with this is now that the text labeling everything is
Yeah, that's okay.
sideways
Yeah.
and mirrored.
Yeah, yeah. So, but anyway, but this is better because when you have B coming in, you see this diode going down here. I mean, you guys have the correct picture in your book. So, let's see. Okay, so when this coming in, you have this two. Right. So that's exactly, you come in from base to emitter, there's one diode, and from base to collector, there's a diode. But then there is also a current source between collector and emitter. So that's the current source here, right? So therefore, you get that exactly equivalent circuit. And this current source is proportional to IS times VB over VT, and VB is given applied between base and emitter. The difference between IC and this one gives you current over here. So yeah, go ahead.
Why do we have, on this equivalent circuit, there's two diodes, but other ones we have just one?
This one just shows you how it operates. Basically,
It's an equivalent.
yeah, well, the other one is a mathematical model, and this one is more like a physics model.
Oh,
Yeah, so this one shows how it
yes,
operates.
I
Yeah,
guess, right.
yeah.
Just represents-
yeah. So yeah, so this is not much, just illustrate between the physics, you know, and how current flows in that circuit. Okay. Now let's Okay, we still have. Got it. So let's talk a little bit about PNP transistor. So a PNP transistor is just a flip of NPN. So instead of having NPN structure, you have PNP structure. So in this PNP structure, apparently you also have two diodes. You have two bipolar junctions, two pin junctions. So that's why it's also called bipolar. But the current directions are going to be very different because the way the diodes are maintained, right? So you have diodes over here, then you have so that's P, and in the middle is N, and this is P. And the symbol for this one is like this. And we have emitter on the top, and then we have a collector at the bottom, we have base over here. So the symbols now, everything is like a flip. So instead of VCE, we call VEC. Instead of VBE, we call VEB, right? And then the current up is IC and IE, and the bottom is current over is IC, and this is IB. So you can see here, you still get a few things the same, which means VEB, you typically has to be larger than 0.7 volts for the circuit to work. And also you have IC equal to beta times IB. And you also have IE equal to IC plus IB. Or in other sense, you can have IC equal to alpha times IE. And here you also have, you can also write IS equal to IS times e to the power VEB or VT. So here, remember this equation here is VEB instead of VBE. So that's the difference. Okay. So now, of course, whether it's PNP or NPN, when this VB is given or VEB is given, you see this is a constant. VT is 25. So if VEB is 0.7 and this is 25, so this gives you a certain number. And when you have a different device material, IS is different and IC can be different. Go ahead.
I noticed one small discrepancy with that drawing. Shouldn't current be flowing out from B instead of in from B?
Yeah, it's flowing out of IB. Right. You're right. You are absolutely right. I'm sorry about that. Yeah, no, you're correct. It's current. It's flowing out of IB. Yeah. Thank you for that. It's great. You guys are very good. Okay, so that's the BJT, P-type of BJT, and in the future we have also we are going to also do some examples on P-type BJT, and sometimes we have them put together. So yeah, we don't learn this in we don't learn that in this class, but in 430, you guys would learn the power amplifiers like Class A, Class B, Class C amplifiers. A lot of them actually are made with BJTs. So those are simple structures. So you still have some BJTs in integrated circuits, but they're rare in the sense that they are used, most of them are going to be used for power amplifiers. Yeah. So in that case, we have BJTs like 1P type, 1N type together to make like a CMOS, we have NPN and PNP, right? So, okay. So for the model, mathematical model for PNP transistor or P-type transistor is very similar to NPN. We have a T model, and then we have a pi model. And the T model, you're right, for the correction, IB actually, flows out. So that's why you get IC equal to IE minus IB. Otherwise, you wouldn't have that equation. As you can see, the only difference here is VEB is VEB instead of VBE, right? Of course, the current source is at the bottom instead of the top, right? So in the NPN, this current source is on top because C is on top. Now E is on top, C is at the bottom, so we move the current source at the bottom. But if you use a pi model, you can see the diodes is above B instead of below B, right? So that's why you need a E voltage to be higher than B to conduct. Okay, this case shows what kind of voltage you need at the E, make the circuit conduct. Right? So if I actually maybe I should draw the NPN type just for comparison. C, B, and E. So this is N type. This is P type. Right? And then this other equivalent circuit is going to be similar. So you have B. It's almost like do you guys see the difference between these two? It is simply just, I mean, MOSFET is the same thing. We just like flip everything like 180 degree. We got that. So this is E up, this is C up. Okay, those are two equivalent circuits. I think that's pretty much for section 1 in the book we covered so far. Just looking at the basic properties of PNP and NPN type of BJTs, and the voltage current relations, and then the equivalent circuit model, mathematical models, and the frequency operations, and so on. Section 2 is more like a recap of the voltage current relations, but then we do kind of different variation for circuits, so we can catch the how to solve problems with real BJTs. Right? So let's dive into that BJT transistor. So I made this little table here just that we want to kind of summarize what are the properties, what are the voltage current relations. So let's do it together. All right, so for the BJT transistors, let me see what I wrote here. We have a couple of important numbers. So for number 1 is VT. So this number is the same for both PNP and NPN type of BJTs. Okay. And then another equation is IS. Well, I'm going to write IS over here. So IS for N type, so this is N type, right? And this is P type, or NPN. Sometimes we call or IS, this is equal to, not IS, I'm sorry, ICs. Now IC, what I wanted to say, IS is something usually given. Okay. So this IS times e to the power VB or VT. And then for the PNP, it's IS times e to the power VEB or VT. So that's the difference between P and anti-BJT, it's either VEB or VBE. And then to be inactive or saturation and VBE. And this says that's the difference. One is VEB, one is VBE. And then for other relations like IC, I equal to beta times IC, and this one is also an IC, and also I equal to IC plus. Oops, no, this is terribly wrong. I'm sorry.
Professor, for
I
the
see.
saturation, is that supposed to be an equal sign, or is that supposed to be there?
Yeah, it can be typically like this. Basically, I mean, we always assume actually 0.7. So IE equal to IC plus IB. Okay, so that's the relation between this. Of course, there's alpha as well. We're not gonna write too much of that. But I also wanted to write like in saturation mode, VCE equal to 0.2 volts. VEC equal to 0.2 volts. In active mode, okay. So these are some basic properties. Now, of course, beta, you guys, possibly typical is 100, things like that. So that can be given as well. And then for the circuit wise, sure.
C minus IB.
IB is flowing out, so we have to define the direction. So IB is in this direction, and IC is this direction. So I is this direction. So if you look at this node, right? So, but here it's this direction here, right? So if you look at a simple node, you will find out that how it works. Okay, so this is the basic circuit when you connect the voltage at the base and voltage at the between the collector and emitter and so on. But so here again, you guys can do exercise using what we just did. And also we want to talk a little bit just a graphical presentation. Remember in the MOSFET, we did a little bit of threshold. You have to be able to about the threshold for the circuit to conduct. So we draw like an illustration. Okay, this is threshold, which has to be about the threshold to work. But then your VDS has to be within a certain range. If your VDS is too low, and it will go to triode instead of saturation mode. So in here, we also have a similar graphical illustration, and this is actually very useful. Just looking at a diode like at the base. So your diode is 0.7. So for the circuit to work, either in saturation or linear mode, the diode has to have a 0.7 volts. So VBE has to be 0.7 volts for this one. Of course, for that one, is VEB has to be 0.7. Now, once VBE is 0.7, you have a base current. Now, for how much current going through collector and emitter, it will depend on voltage of VCE. So if VCE is more than 0.3, like 0.3, you are in active mode. But if VCE is less than 0.3, you actually are squeezed into saturation mode. Okay. So the VCE can be 0.7 exact, or it can be more, right? Because look, the way that we draw here, active mode does not have up limit. So you can go above 0.7. As long as it's more than 0.3, it will go to active mode. As long as you fall 0.3, it's between the age. It's at age between saturation and active. When it's going to full saturation, it's 0.2. Now, similarly on this one, is you look from the top. So from VE to VB, it has to be 0.7, okay? And once that reaches 0.7, and this BJT conducts. Whether it's in active or whether it's in saturation, depending on the voltage between E and C, so VCE. So if VEC is 0.3, it's between saturation and linear mode. But if VEC is more than 0.3, it's active. And it can be much more. It can be go like 0.7, 0.8, 4, 5, 6, 7, depending on what voltage you have at the bottom. So this is just an illustration purpose only. It doesn't really do a lot of those. And finally, this table summarizes the relations that we just had on the previous slide. Of course, the importance is also given, like VT is 25 millivolts, for example, is given, and you get a couple of relations between IC, IB, and IE with beta and alpha, how to calculate, and also in the beginning, how to calculate IC over here. So IC, IS over that, okay? So yeah. So this is a very important slide, and you guys need to memorize this. So now we're going to dive into another example before we finish today's lecture. So in this example, we have a BJT, and that BJT base is grounded. Collector is connected to 15 volts through resistance of RC. And base emitters connect to minus 15 volts through a resistance of RE. And what it says that beta is 100 is given. And it also says that when VB is 0.7, IC is 1 milliamps. Okay, so up to this point is what is given. So from the given conditions, what can you guys infer? What does it mean? So when VB is 0.7, IC is 1 milliamps. What does it tell you? Without looking further to the equation, we just say, okay, when VB is 0.7, IC is 1 milliamps. Go back to the equation here. Look at the very first equation. What does it say? IC is given, VB is given, VT is constant, which means you can solve for IS. Okay, so that's what it says, right? You can solve for IS. Okay. Of course, and then what it says here, it was asking you, now I want you to have 2 milliamps current flows through the collector, and a voltage of 5 volts appears at the collector. 5 volts at the collector, not the power supply, but at the collector, which means it's the point below RC. So this equation is so confusing that people will say, okay, if, like, for example, we can start doing step by step. So if IC is 1 milli, oops, IC is 1 milliamps. What do you get for VC directly? It's 15 minus RC times IC, right? But the problem is we don't know RC, so we cannot calculate VC. However, if VC is 5 volts And then we can calculate RC equal to 15 minus 5 divided by IC. It's 10 kilo ohms.
Assuming it's fine.
Well, 5 was given.
Oh,
Well, that is wrong because what it says here, it says 2 milliamps current. Now we're actually having trouble because it's 2 milliamps current. In fact, if it's 2 milliamps current 5 volts, then that calculation is actually was based on 1 milliamp, which apparently is not going to work, right? So what we are saying that, okay, if it's 2 milliamps at 5 volts, which means we're going to have RC equal to 15 minus 5 divided by 2 milliamps. That gives you 5 kilos. So now you want to ask me, oh, what is going on? Then you say RC is 10. Now you are seeing RC is 5. Which one is correct?
the,
Well, I can tell you the second one is correct. The reason is that,
we don't know DC in the first.
right, you're right. The VC was given at 2 milliamps. It was not given at 1 milliamps. We don't know. So the first calculation apparently was wrong. So this one was wrong, but this one is correct. But of course, it asking you to design the circuit, which means we need to find RE as well. But now we're going to have trouble because we don't know RE. So we need to find out RE. How do we find RE? Well, there's one simple way, because I want to do this in a different way so you guys understand what we're doing. So if we assume beta is infinity, but of course beta is not infinity because we're given at 100, right? So, but I'm just doing some like manipulation so that we can see what we're going to get. So if we do that, then IE is going to be same as IC, 2 milliamps. So if IE is 2 milliamps, we also have to assume VBE is 0.7. So here. So then VE is going to be minus 0.7, right? Because it's active, so we're going to do these assumptions. So if VE is 0.7, we know that IE equal to VE minus 15, right? So plus 15 divided by RE. So now we got RE equal to IE going to be minus 0.7 plus 15 minus 0.7 plus 15 divided by 2 milliamps. That gives you 14.3. That gives you 7.15 coulombs. Now, yeah, we do get some solution, which is not terribly wrong. But the problem is that we didn't get to use the given condition. Beta is 100, VB is 0.7 at IC 1 milliamp. We didn't use it, right? So which means somehow we got some solution, but we didn't use the given condition, which means this problem, somewhere. And now, of course, the reason that we didn't use it because we made some assumption. The assumption we made is beta infinity, so IC is equal to IE, and also we assume VB is 0.7. So probably at this point, you already got some idea, right? Because you neglect beta. That's why you got IC-IE. So which means in this equation that IE shouldn't be 2 milliamps. It should be something else, right? It should be IC plus IB, okay? So that's one thing. another thing is that VBE, you assume 0.7, but it may not be 0.7 because what it says here is if it's 1 milliamp, it's 0.7. Now it's 2 milliamps, it's not going to be 0.7, it's going to be actually different. So that's where we have to, well, let me go back to that slide. So in this case, you know, in fact, we can calculate IB equal to IC over beta. So that's easy one to calculate. So it's going to be 10 micrograms. And then IE can be accurately calculated as IC plus IB. It's 1.01 milliamp or 2.02 milliamps. Zero 0.02 milliamps. So this is going to be 2.02 milliamps. So this number is actually correct. So this number is correct. So this one is correct. But this one here, so that one is approximate. It's not accurate. Huh?
Still haven't five, we haven't still found RE, which is what we're.
We found IE, but we didn't find RE yet. We found IE, which is 2.02. So what I'm saying that this number is correct. Yeah, but we have not found RE yet. But the RE we found here is not accurate. It's an approximate solution, right? So how do we find the accurate solution? Well, because it was given VBE 0.7 is to 1. IC is 1 milliamp. So using ISQ2 IC equal to IS e to the VBE times VT, we can do we can find IS equal to e to the power VBE or VT divided by IC. So we can find IS. This is a certain number. I don't remember the.
Why are we finding IS?
Well, you're finding why IS because you want to find IC when VBE is 2 milliamps, right?
We find VBE.
Well, yeah, you find VBE. See, in this case, you have VBE equal to VT times log V IC over IS. So IC is 2 milliamps, right? IS is here. So IC is here, IS here. So what we found, let me see what we got. VBE is 0. Okay. So I found IS to be 0.69 times 10 to the 15. So I found IS. So I plug in IS and IC and VT. I found VBE to be 0.17 volts. So this is larger than 0.7. Yeah. No, actually, you're right, not correct. I wrote it the other way around. So it's going to be IC over. Thank you. Yes. Yeah, we all make mistakes, and me too. So, and number 4, now you got RE equal to, so from here, you got VE equal to minus 0.717. So now you have 0.717 plus 15 divided by 2 milliamps, and you got a number which is 7.07 kilo ohms. So comparing to the other value was 7.15 kiloohms. Which is not too bad. Right, so this actual value, this is approximate value, right? Yeah, go ahead. Oh, 2.02, you're right, 2.02. I'm sorry, yeah, 0.2. Yeah, anything else?
So we're just assuming that the saturation voltage stays constant when we change their other values.
No, saturation voltage, no, not saturation voltage. This is actually in active mode. Yeah, the saturation current change. Yeah, that's constant. That's a device material property. It doesn't change. Yeah. Okay. Chris, I'll see you next week.